The last category of reactions that we're going to learn about are oxidation-reduction reactions. Oxidation reduction is called redox for short, and it's reactions where electrons are transferred from one substance to another. The word oxidation means loss of electrons, and the word reduction means gain of electrons. We're going to want to be able to identify what substances are oxidized and what substances are reduced in order to predict redox reactions. There are many examples of redox reactions all around us every day. For example, when iron combines with oxygen to form rust or iron oxide, the iron becomes oxidized in the process. Hydrocarbons, or substances that only contain hydrogen and carbon, undergo combustion, which is an oxidation reaction. If you've taken biochemistry or biology, you will eventually learn about beta oxidation. And if you take Chemistry 112, we'll spend a bit of time learning about electrochemistry and batteries. An easy way to remember oxidation and reduction is to use Leo the lion says grr. Leo, or loss of electrons, means oxidation. Grr, gain of electrons, means reduction. You're going to want to commit these definitions to memory. Oxidation and reduction always occur together. Let's consider the oxidation of three different reactions, one starting with an anion, one starting with a neutral atom, and one starting with a cation. In all of these reactions, electrons are listed on the product side. When something gets oxidized, electrons are always a product, meaning that they're lost. If we start with something with a negative charge, when it loses an electron, it'll become a species that is neutral. If we start with something that is neutral, when it loses an electron, it'll become a species that is positive. If we started with something positive and it loses an electron, it'll become a species with a +2 charge. Any of these reactions could be flipped around and written in the opposite direction, and then they would be reductions. If we write the first one, neutral A plus an electron, which has a negative charge, once it gains that negative charge, now you'll have produced a species that has a negative charge itself. This would be an example of a reduction reaction. In reductions, the electrons are on the reactant side. Any reaction will become an oxidation if we flip it around, or if we flip our oxidations around, they all become reduction reactions. An example of redox that we've seen before is the formation of ionic products. For example, the formation of sodium chloride, or common table salt, is actually a redox reaction. In this reaction, sodium metal actually loses electrons to become a sodium ion. So sodium gives up its one valence electron to become Na+. Chlorine, on the other hand, has 7 valence electrons, and it gains that one electron from sodium to become the chloride anion, or Cl-. There is a change in the charge of our reactants going to products. Therefore, it's a redox reaction. If we look at the balanced equation, sodium on the left has no charge. Chlorine's diatomic, and that also has no charge. But on the right-hand side, if we break apart our products, sodium is a +1 and chlorine is a -1. We formed charged species from neutral species. Therefore, electrons must have been transferred. Shortly, we're going to learn some rules that will allow us to track changes in the oxidation numbers or oxidation states of our reactants and our products. With ionic compounds, it's fairly straightforward, especially if they're one of our representative elements that we're able to predict the charges of. For example, if we were to look at our sodium becoming a sodium ion, we can see that for that process to happen, one electron must have been lost. When we look at our chlorine becoming a chloride anion, in order for that to happen, since chlorine is a diatomic molecule, every one will form 2 chloride anions. 2 electrons must have also been gained in the process for each chlorine to develop a negative charge. Electrons are a product when something becomes oxidized, and electrons are a reactant when something becomes reduced. We're going to learn a series of rules that will allow us to track these changes eventually. But for these ionic compounds, we can simply look at the charges they would form according to the group number on the periodic table. There are a few other terms to learn when describing redox reactions. The first one is an oxidizing agent, or an oxidant. That is a substance that accepts electrons and causes oxidation in another substance. The oxidizing agent gets reduced itself. A reducing agent, on the other hand, or reductant, is a substance that will give up electrons in a chemical reaction. It will be getting oxidized itself, so it causes reduction in something else. A reducing agent will lose electrons to become oxidized, and an oxidizing agent will gain electrons to become reduced. The reducing agent gives up its electrons to the oxidizing agent. Oxidation does not occur without reduction. The two always happen together. Let's practice using our new definitions. In the reaction between magnesium and molecular oxygen, the product is magnesium oxide. Which element is oxidized and which is reduced? What are the oxidizing and reducing agents? We're going to try to write a balanced equation for this reaction first. We know magnesium is reacting with molecular oxygen, and what that means is it's O2. We know that's one of our diatomic molecules. And the product is going to be magnesium oxide. If we write a correct formula for magnesium oxide, it would be MgO. We can then balance this reaction. We have 2 oxygens on the left and only 1 on the right, so we're going to put a 2 out in front of the magnesium oxide. And we're also going to need a 2 out in front of the magnesium. Then if we consider the charges of the species on the left-hand side, or our reactants, magnesium has no charge. It's a free element. O2 is also not a charged species. But when we formed our products, magnesium oxide, the charge on the magnesium is a 2+. The charge on the oxygen, or oxide, is O2-. We formed cations and anions throughout this process. So we did change charges, therefore transferred electrons. Magnesium went from a 0 charge to a +2. In order for it to increase in charge, it must have lost electrons. Losing electrons is called oxidation. Our oxygen went from a 0 charge down to a -2 charge. This must have gained electrons in order to decrease in charge. Gain of electrons is defined as reduction. This is how we can identify which substance was oxidized and which substance was reduced. So our magnesium was oxidized. Our oxygen was reduced in the process. And when defining the oxidizing and reducing agents, those are going to be the exact opposite of what we just determined. The magnesium, since it was oxidized, would be our reducing agent, and our oxygen will be our oxidizing agent. Let's try another example. Identify the substances oxidized and reduced and the oxidizing and reducing agents in the reaction of aluminum and chlorine to form aluminum chloride. Aluminum is a metal, and chlorine is another diatomic molecule, so it'll exist as Cl2 naturally. And the correct formula for aluminum chloride will be AlCl3. We also want to balance this reaction. We're going to need to place a 2 out in front of the aluminum chloride, a 2 out in front of the aluminum, and a 3 out in front of the chlorine. To figure out who was oxidized and who was reduced, we have to think about how the charges in the substances changed. Aluminum is not a charged species, and chlorine is not a charged species. Our aluminum chloride is. Aluminum in compounds forms a +3 charge. Chloride is a -1 charge. Tracking our changes then, aluminum went from a 0 charge to a +3 charge. It must have lost electrons to do that, therefore it was oxidized. The chlorine went from a 0 charge to a -1. It must have gained electrons to get more negative, or it was reduced, we say. So the aluminum was oxidized, the chlorine was reduced, and our agents will be the opposite. Aluminum was our reducing agent, and chlorine was our oxidizing agent. Since not all reactions produce ionic products, that means it will be sometimes harder to track the changes in the electrons. For example, sulfur plus oxygen forming sulfur dioxide is also a redox reaction. But since we have two nonmetals together, this is not an ionic product. This is a molecule. It's not easy for us to look at this and determine how the electrons were transferred. Therefore, we need to develop a set of rules in order to track the changes in compounds that are not ionic. This brings us to oxidation numbers or oxidation states. These are a set of bookkeeping rules that will allow us to keep track of our electron transfers in redox reactions. The oxidation number of an element in a compound is the charge the atoms would possess if the compound was ionic. So even for molecules, we're going to pretend that it's an ionic compound and assign them a set of oxidation numbers in order to track the electrons. A redox reaction is a chemical reaction where there's changes in those oxidation numbers. Some oxidation numbers will go up and some oxidation numbers will go down. This is how we'll predict what's being oxidized and what's being reduced in a chemical reaction. You have a handout on Blackboard for rules for assigning oxidation numbers, and I suggest you print that out and keep that next to you while you're practicing on the next few slides. You're not going to have these rules with you on a quiz or exam, so you're going to need to practice using them. Eventually, they'll become second nature. The rules are ordered in terms of their rank, meaning Rule 1 is ranked higher than Rule 8. Let's go through them. Rule 1. Oxidation numbers must add up to the charge on the molecule, formula unit, or ion. Rule number 2. All of the atoms of free elements have an oxidation number of 0. Rule 3. Metals in groups 1A, 2A, and aluminum have +1 and +2 and +3 oxidation numbers respectively. Hydrogen in compounds has a +1 oxidation number. Fluorine in compounds has a -1 oxidation number. Oxygen has a -2 oxidation number. The other halogens in group 7A have a -1 oxidation number. Group 6A elements have a -2 oxidation number, and group 5A elements have a -3 oxidation number. Sometimes we'll find that these rules might conflict. If they conflict, we want to apply the rule that comes higher on the list first. Let's try a few examples to learn how we assign oxidation numbers to each atom in the following compounds. If we have something like nickel 2 chloride, or NiCl2, we want to break this up into the individual elements that are composing the compound and think about each of them separately. We don't have a rule in our oxidation numbers for nickel, so we're going to have to start with chlorine. Chlorine in a compound has an oxidation number of -1. From our subscript, we can see that there's 2 chlorines in this compound, so the total of the chlorines will be -2. The sum of our oxidation numbers has to sum to 0 because this is not a charged compound. That's rule number 1. Therefore, the nickel must have an oxidation number of +2 in this compound. How we answer what the oxidation numbers are is we list them out. Nickel is a +2 and chlorine is a -1. We don't care about the sum of the chlorines, we only care about what the individual atom is. We only had to figure out the sum so we could determine the oxidation state of the nickel. Let's try the next one. Mg2TiO4. If we break this up into our individual elements making up the compound, we have a few rules. We have a rule for magnesium and we have a rule for oxygen. Oxygen in compounds has an oxidation number of -2. And there's 4 of them in this compound, so the total oxidation number for the oxygens is -8. Magnesium is going to have a charge of +2 since it's a group 2A metal, and there's 2 of them in this compound, so the total of the magnesiums is +4. The sum of all the oxidation numbers must add to 0 since this is another neutral species. Therefore, the titanium must have an oxidation number of +4 in this compound. So we have magnesium with an oxidation number of +2, titanium with an oxidation number of +4, oxygen with an oxidation number of -2. H3PO4 is our next example. Break this guy up into its individual elements. We have rules for hydrogen and for oxygen, so we'll save the phosphorus for last. Hydrogen in a compound is +1. We have 3 of them in H3PO4, so the total of the hydrogens will be +3. Oxygen is a -2 in this compound. There's 4 of them. The total of the oxygens will be -8. The sum of the oxidation numbers must add to 0, so the phosphorus must be +5 for its oxidation number. So we have hydrogen being a +1, phosphorus with a +5, and oxygen is a -2. That's how we answer what the individual oxidation numbers are. Our next example is vanadium 3 acetate, and this one contains a polyatomic ion. Acetate is a polyatomic ion, and it's easier to consider this as a unit first when determining the oxidation numbers. So let's think about what vanadium is and what acetate is, and then we'll break out the acetate separately. Acetate has a charge of -1, and the oxidation numbers of all the acetate must add to the charge on that ion, so they'll all add to -1. There's 3 acetates in this compound, so the total of the acetates will be -3. Since the sum of the oxidation numbers for this compound must add to 0, the vanadium must also be +3. Now we can consider the acetate separately. Acetate is C2H3O2 with a -1 charge. When we break this up, that -1 charge tells us that's going to be the sum on all of our oxidation numbers. Oxygen is -2 in a compound. We have 2 of them, so it'll be -4 for the total. Hydrogen in a compound is +1. We have 3 of them, so it'll be +3 for the total hydrogens. And the sum of our oxidation numbers has to add to the charge on the compound. The charge on acetate is -1, so our sum has to add to -1. Right now we have +3 and -4. The oxidation number on carbon, therefore, must be 0 in this compound, since the hydrogen and oxygen are already adding up to -1. Oxidation numbers are not charges. Sometimes they're the same as charges, but they are just used as a bookkeeping method to keep track of electron transfer. So vanadium has an oxidation number of +3, carbon 0, hydrogen equals +1, and oxygen equals -2. Our last example is the ammonium ion, NH4+. If we break this apart, hydrogen in a compound has an oxidation number of +1. There's 4 hydrogens, so +4 total. The sum of our oxidation numbers in this case has to add to the charge on our ion. It's not neutral, so it'll add to +1. Our nitrogen, therefore, must be -3. So our oxidation numbers will be nitrogen is -3, hydrogen is +1 in the ammonium ion. Let's try a few more examples. Cadmium sulfide. If we break this up, we're going to have sulfur, which is going to have an oxidation number of -2. That would be the rule. And they're going to have to add to 0 since the compound's neutral, so cadmium must be a +2. So cadmium, oxidation number of +2, sulfur, oxidation number of -2. Our next one, S2O3 2- is a polyatomic ion called thiosulfate. We're going to break this up and look at it individually. Oxygen in a compound is -2. There's 3 oxygens, so the total is -6. This time, our charges or our oxidation numbers must add to -2. So our sulfurs must be +4 together. We have 2 sulfurs in this compound, and we want to determine the oxidation number of just one sulfur. So we're going to take our +4 and divide by 2. That gives each sulfur an oxidation number of +2. When listing the answer, we would say sulfur equals +2, oxygen equals -2. Na2Cr2O7, the name of that is sodium dichromate. We're going to want to break this up into the 3 elements, sodium, chromium, and oxygen. We have a rule for sodium and we have a rule for oxygen. Oxygen's -2 in a compound. There's 7 of them, so the total is -14. Sodium's a group 1A metal. Its oxidation number is going to be +1 in a compound. We have 2 of them, so the total sodiums will be +2. The sum of the oxidation numbers should add to 0, so the total for the chromiums should be +12. We only want to look at one chromium though, so we're going to need to divide by 2, and that means each chromium has an oxidation number of +6. Sodium is a +1, chromium is a +6, and oxygen is a -2. FeSO4, or iron 2 sulfate, is our next example. And this is a good one to break up into our polyatomic ion sulfate component first, like we did with our vanadium acetate. So first let's look at our sulfate. Sulfate's a polyatomic ion. The total oxidation numbers are going to add to the charge on the ion, which is -2. That means the iron in this compound must be a +2 charge, since the overall compound is neutral. Now if we take the sulfate out and figure out the oxidation numbers separately, sulfate is SO4 2-. Our oxygen will be a -2 in this compound. There's 4 of them. The oxygen total will be -8. The sum of the oxidation numbers are going to add to the charge on the ions. They're going to add to -2. That means the sulfur must be a +6. So our oxidation numbers in this example are iron will be +2, sulfur will be +6, and oxygen will be -2. Our last example is the nitrate anion, NO3-1. If we break this up here, we're going to have oxygen being a -2. There's 3 of them, so -6 for the oxygens. The sum in this case is going to add to -1 because of that charge on the ion. So nitrogen in this compound must be a +5 oxidation state. So nitrogen is +5 and oxygen is -2. After we use our rules for determining oxidation numbers, we can now redefine oxidation and reduction. Oxidation involves an increase in the oxidation number. Reduction involves a decrease in the oxidation number. If we have molecular hydrogen combining with molecular chlorine to form hydrogen chloride, we can see hydrogen went from a 0 oxidation state to a +1 oxidation state. Since it increased, hydrogen was oxidized. Our chlorine went from a 0 oxidation state down to a -1 oxidation state. Since there was a decrease in oxidation number, we can say the chlorine was reduced. In this example, we want to identify the substance oxidized, the substance reduced, as well as the oxidizing and reducing agents. This example looks a lot more complicated than our first couple. We're going to have to apply our oxidation rules in order to determine the oxidation number of everything on the reactant side and everything on the product side. Once we do that, we can determine what oxidation numbers have increased and what oxidation numbers have decreased. If we start with potassium chloride, chlorine in a compound has an oxidation number of -1. Potassium will have an oxidation number of +1. Manganese 4 oxide. Oxygen has an oxidation number of -2. There's 2 of them, so the total is -4. The sum should be 0, so our manganese will have an oxidation number of +4. H2SO4, oxidation for oxygen is -2 in a compound. There's 4 of them, so the total is -8. Hydrogen is 1 in a compound. There's 2 of them, so the total is +2. The sulfur must be +6 in this compound. Moving to the product side now, potassium sulfate. Oxygen is a -2. There's 4 of them, so -8. Each potassium is a +1, and there's 2 of them, so +2. Sulfur over here is also a +6, so it did not change in that compound. Manganese sulfate is an example where we have a polyatomic ion with a transition metal. So if we break this up like this first, the sulfate will be -2, the manganese must be +2. Break the sulfate out separately, SO42-. That would mean that the sulfur and the oxygen we can figure out separately now. Oxygen is -2, 4 of them, so -8. The sum must be -2, so sulfur would be +6. Chlorine is a free element. It's not chemically combined with anything else, and it's in its natural state. Therefore, its oxidation number is 0. And in H2O, oxygen will be a -2, and hydrogen will be a +1. There's only 1 oxygen, so the total is -2. There's 2 hydrogens, so the total is +2 here, summing to 0. To track the changes, we need to see what is different on the reactant side going to the product side. Notice that potassium is a +1 on the left, and it's still a +1 on the right. Manganese started in a +4 oxidation state, and it went down to a +2 oxidation state. If it decreased in oxidation number, therefore it must have been reduced. Oxygen's a -2 on the left, and it's a -2 everywhere on the right still, so it did not change. Hydrogen was a +1 on the right and the left, everywhere that hydrogen was found. It also did not change. Sulfur was a +6 on the reactant side. It was a +6 in every compound on the product side. But our chlorine started as a -1 on the reactant side, and it became a 0 charge or 0 oxidation number on the product side. Therefore, our chlorine went from -1 oxidation state up to a 0 oxidation state. So it increased in oxidation number, which means it was oxidized. When we figure out what substance was oxidized or what substance was reduced, we're talking about the entire thing. We can't just pluck the manganese out of the manganese 4 oxide, or we can't just pluck the chlorine out of the potassium chloride. Therefore, potassium chloride contains our chloride. So this substance was reduced. The manganese 4 oxide contains our manganese. This substance was oxidized. And remember, when we're determining the oxidizing and reducing agents, those are going to be the exact opposite. What was reduced will also be our oxidizing agent, and what was oxidized will also be our reducing agent. So our potassium chloride was reduced. It's our oxidizing agent. Our manganese 4 oxide was oxidized, and therefore it was our reducing agent. Let's try another example. SnO2 plus 2C gives us SN and 2CO. So that's tin 4 oxide plus carbon gives us tin and carbon monoxide. We want to track the changes in the oxidation numbers. Oxygen in a compound is -2. There's 2 oxygens, so -4. Tin must be a +4 for it to sum to 0. Carbon is a free element, not combined with anything else, so its oxidation number is 0. Tin, same thing. Oxidation number is 0 when it's alone. And then carbon monoxide, oxygen is a -2, and so carbon must be a +2, so they sum to 0. Tracking our changes, tin went from a +4 down to a 0 oxidation state. Carbon changed, it went from a 0 oxidation state up to a +2. Tin, if it went from a +4 down to a 0, it decreased its oxidation number, therefore it must have been reduced. Carbon, going from a 0 up to a +2 oxidation state, increased in oxidation number, therefore we say it was oxidized. The substance that was oxidized and the substance that reduced will come from our reactant side. Carbon, we said, was oxidized, and then the tin 4 oxide was reduced. It's the entire substance. This also means that our tin 4 oxide is our oxidizing agent, and our carbon, which was oxidized, is our reducing agent. Looking at the next example, we have ammonia plus oxygen forming nitrogen monoxide and water. In our ammonia, hydrogen is +1. The total is +3. So the nitrogen must be a -3. Our oxygen is a free element by itself, so the oxidation number is 0. Nitrogen monoxide, oxygen is -2. Nitrogen must be +2, so they add to 0. And in H2O, our oxygen is -2. There's only one of them, so the sum of the hydrogens is +2, and each hydrogen will be +1. Looking at our changes, our oxygen went from a 0 down to a -2. It actually went to a -2 in both compounds, so it was the same. And our nitrogen went from being a -3 on the reactant side up to a +2 on the product side. So our changes are our oxygen went from 0 down to -2, so it decreased in oxidation number, therefore it was reduced. Our nitrogen went from a -3 oxidation number up to a +2 oxidation number. It increased in oxidation number, therefore it was oxidized. Since our NH3 contains our nitrogen, which was oxidized, this whole substance, we say, was oxidized. The oxygen, we say, was reduced because we know it went down in oxidation number. Our oxidized substance is going to be our reducing agent, and our reduced substance is going to be our oxidizing agent.